In this video, I'll show you what a moment is. I'll explain moments around the origin and mean, and how to find moment generating functions. The most common definitions you'll come across for moments include the first moment, that's the mean or average. The second moment is a measure of how wide a distribution is, that's the variance. For most basic purposes in calculus, statistics and physics, these loose definitions are all you'll need. However, it's important to know there are two different kinds of moments. Raw moments, those are moments about zero, and central moments. They are defined differently. The nth moment about an origin of a random variable x. An example is the mean, which is the first moment about the origin. Then you have the nth moment about the mean of a random variable x. An example is the second moment about the mean, and that's the variance. The general formula for the nth moment is this geometric series. You may have covered geometric series already in algebra or calculus. If you didn't or don't remember how to work one, don't worry too much. In most cases you won't actually have to perform the calculations. You just have to have a general grasp of the meaning. The formula might look a little daunting, but all you have to do is replace that exponent r with the number of the moment you're trying to find. Let's take a look at an example. For the first moment, you're going to replace r with 1. The first moment around 0 for discrete distributions is this summation. It's identical to the formula to find the sample mean in statistics. You add up all of the values and divide by the number of items in your data set. For continuous distributions, the formula is almost the same, but it involves an integral. I'll show you an example of integration in just a little bit. The second moment around the mean is equal to the variance. That sigma notation there means to add up. In practice, only the first two moments are used in statistics, but you'll come across several more in physics. The third moment is skewness. You can see I've replaced r here with 3. Skewness gives you information about a distribution's shift or lack of symmetry. Distributions with a left skew have long left tails, and distributions with a right skew have long right tails. The fourth moment is kurtosis. Kurtosis tells you how a data distribution compares in shape to a normal or Gaussian distribution. That distribution has a kurtosis of 3. In this image, the distribution on the left has positive kurtosis. Positive kurtosis means there's a lot of data in the tails, and the distribution on the right has negative kurtosis. Negative kurtosis means there's not much data in your tails. Again, that's compared to a normal distribution. Higher order terms above the fourth are difficult to estimate and equally difficult to describe in layman's terms. For example, the fifth R measures the relative importance of tails versus the center. For example, the mode or shoulders in the cause of a distribution's skew. A high fifth means there's a heavy tail and little mode movement. A low fifth means there's more change in the shoulders. Higher order moments are sometimes calculated from the definition. Other times they're calculated with a moment generating function. Moment generating functions are a way to find moments like the mean or the variance. They are another way to represent a probability distribution with a simple one variable function. Every probability distribution has a unique MGF. The MGF is a computational tool. You can think of it as a formula in the same way that y equals mx plus b allows you to create linear functions. The MGF formula helps you to find moments. For a discrete random variable, you'll use summation. For continuous random variables, you need integration. For this formula, f of x is the PDF of x, and the integration range will change depending on what range your function is defined for. Let's take a look at the MGF for the exponential distribution. We begin with the PDF for the exponential distribution. It's defined for values greater than 0, which means we're going to change the limits of integration from 0 to infinity. The first step is to plug our PDF into the formula. So I'm going to replace f of x with the PDF for the exponential distribution. I'm going to pull lambda out in front and rearrange the right-hand side. We want our integral to converge, so we must set the condition that t minus lambda is less than 0. When I integrate this function, I get 1 over t minus lambda e to the t minus lambda x, and I'm going to evaluate that between 0 and infinity. At 0, my function is going to be 0, and at infinity it's 1 over t minus lambda. That simplifies to our MGF of lambda over lambda minus t. I hope you found the video helpful. Please take a moment to subscribe, and I'll see you in the next video.